wonder to yourself, why in the world is it that when fructose 1,6-bisphosphate is cut in half, we get these two different molecules? So we get DHAP, so this is a ketone, and glyceraldehyde 3-phosphate and aldehyde. So I'm going to go over that reaction mechanism with you guys because I think it'll make more sense once we actually go over the mechanism. So the reason why we end up with an aldehyde and a ketone is because the enzyme aldolase, you don't actually have to know the name of this enzyme for the exam, but the enzyme aldolase uses what we call an aldo cleavage reaction mechanism to cut this molecule in half. So remember that an aldo is characterized by kind of having the following properties. You have a C-double bond O group, and then 2 carbons away, so alpha carbon, beta carbon, you have an alcohol attached to that carbon. And so, if you have this situation, the molecule can undergo an aldo cleavage, where we actually cleave the bond between the alpha and the beta carbons. And so this is what it's going to look like. So this is fructose 1,6-bisphosphate. And let's just assume this is some type of general base catalyzed reaction. What happens is a base is going to abstract the proton off the alcohol, and then there's going to be an electron shift. So these electrons between the oxygen and the hydrogen, it's going to go between carbon and the oxygen, so that'll make a double bonded carbon. This is going to then cause the bond between the alpha and the beta carbons to break. So these bonds are going to be shifted over here. And remember that carbonyls are electron withdrawing, so then these electrons are going to go into the oxygen. So what happens next is you have proton transfer. So the proton's going to protonate this intermediate, this carbanion ion. And what's going to result is basically, right, the substrate that's now been cut in half. So the bottom half is the aldehyde. I'm just going to draw it to look like that. And then the top half is going to be an alcohol. Okay. So this is where you have this is where it makes the glyceraldehyde 3-phosphate, and then dihydroxy acetone phosphate. Now here's the thing about this reaction is, if you can imagine that one of the intermediates that's going to have to form is this. When the electrons are being withdrawn to the oxygen, it forms this carbanion intermediate, which is very unstable. So that is a very high energy intermediate that does not like to form. And so we're going to talk about how the enzyme aldolase uses something called a shift base in order to be able to stabilize this reaction. Okay, so it's going to not actually form this intermediate, it's going to form something else to make this reaction go. The other thing you might be thinking to yourself is, well wait, there's lots of molecules in glycolysis that are aldo. For example, we have here glucose 6-phosphate, right? That's made in reaction 2. So why isn't glucose 6-phosphate, why doesn't that go through a cleavage reaction? Because we have kind of the here's our carbonyl group, here's our alpha carbon, and here's our beta carbon, right? So we have the OH group at that beta carbon. And so, in theory, we could have an aldo cleavage reaction that could break the bond between carbon number 2 and carbon number 4. Why doesn't that happen? Or is there a rationale for why that doesn't happen in glycolysis? Yes, Julia.
Maybe the intermediate is stable because it has a hydrogen off the carbonyl carbon that wouldn't be able to withdraw some of the, or handle the charge on the oxygen.
That is a good guess. I actually think, though, that it'd actually be easier to form a carbanion intermediate here because of the fact that here you have a negatively charged phosphate group. So, I mean, that's my guess. But can you guys just think of just sort of just a logical reason of like why not in terms of what happens during glycolysis or what's sort of the point of that glycolysis? Yes.
It's to turn the sugar into energy. If you do that for glucose 6-phosphate, you can't finish the process.
Exactly, right? So part of it is we needed to be able to make 2 glyceraldehyde 3-phosphates. And then the glyceraldehyde 3-phosphates, right, which are they're 2 3-carbon molecules, they're going to be converted to pyruvate, and those reactions are going to generate ATP. Here, what you'd make is a 2-carbon intermediate and a 4-carbon intermediate, and you would not be able to carry those forward in glycolysis. Okay. So now I want to talk about the aldolase reaction and how it uses different parts of the enzymes to be able to catalyze the reaction. So this is going to the handout on glycolytic mechanisms and the pentose phosphate pathway that you guys printed out last week. We are not going to go over reaction 2. I'm not going to test you on it, but if you're interested, I suggest you take a look at the reaction in your book. Instead, we're going to go straight to the next base, or the next page, which is Schiff base. So, Schiff base are, in my opinion, really cool. They're what we call electron sinks, meaning they're going to be sort of places for electrons to go. Now, let's think about just sort of a reaction in which a nucleophile attacks a carbonyl carbon. So the carbonyl carbon is going to be an electrophile. So this is going to cause the electrons to go up into the oxygen, and it forms this intermediate. So this is a unstable carbanion intermediate, energetically unfavorable. What a Schiff base does is it provides a place for electrons to go in a nucleophilic attack. So let's imagine we have a Schiff base. This is actually a protonated Schiff base. And we have kind of a same type of scenario. We have a nucleophile. The nucleophile can attack the electrophilic carbon, and the electrons, those electrons can go into the nitrogen to yield this intermediate, which is much more stable than the unstable carbanion intermediate. So this is sort of one way that enzymes can help to catalyze the reaction, so lower the energy of the transition state, is by forming a Schiff base with the substrate. And so one great example of this is the aldo cleavage reaction, so the aldolase enzyme. It's going to do this with fructose 1,6-bisphosphate to be able to catalyze the aldo cleavage. this looks like really complex, but we're just going to break this down step by step. You'll see it's not too bad. So here's the reaction. We have aldolase. Aldolase is going to take fructose 1,6-bisphosphate and bind the substrate into the active site and then open it up. So it's going to linearize the sugar. So we have now the linear form of fructose 1,6-bisphosphate. Now within the active site, there is a lysine residue. So that lysine residue is going to have an important role in that it's going to form a protonated Schiff base with the substrate. So what happens is the amino group is going to attack the carbonyl carbon on carbon number 2. This is going to push the electrons into the oxygen. And then on oxygen, the electrons on the oxygen are then going to steal a proton from a different residue that's in the active site. So this residue is going to act as a general acid. So then after this, a proton from the solvent comes into the active site, and the alcohol on this intermediate, so now we have a covalent enzyme substrate intermediate. Just going to write IM. That alcohol is going to become protonated, and a molecule of water is then going to leave the active site. Hold on, let me So this is kind of actually skipping a couple steps. So the way that this is drawn, the alcohol becomes protonated. So then we form oxonium, is that the word? An oxonium ion. Okay, and then there's an electron shift. So these electrons between the carbon and the oxygen is going to form a bond between the carbon and the nitrogen here to make a double bonded carbon-nitrogen bond. And then water molecule leaves. Okay, so now we have our protonated Schiff base. Okay, and remember, this protonated Schiff base, this is going to act as our electron sink for catalyzing the aldo cleavage reaction. So within the enzyme, there's a general base. So this is going to be base catalyzed. It's going to abstract a proton from the alcohol group on carbon number 4. So there's going to be an electron shift. So the electrons are going to go between the oxygen and the carbon to make a C double bond O. This is going to then break the carbon-carbon bond. And electrons are then going to go into the nitrogen. So this is the Schiff base stabilizing the intermediate. Yes?
In the step when water came out, where did the second hydrogen come from?
That is actually coming from the environment. So it's just coming from the solvent. Yeah. Okay, so this is essentially exactly what I showed here. This is the same exact thing as what I showed on the board, except these electrons, they have somewhere to go now because there's a Schiff base there instead of forming that carbanion intermediate. So what's happened now is we have the first product that's released. This is glyceraldehyde 3-phosphate, and a part of the enzyme is still or part of the substrate is still attached to the enzyme. And so the next step is there's just a redistribution of electrons. So we're going to remake the protonated Schiff base. So the electrons from the nitrogen are going to go between the nitrogen and the carbon. And then these electrons are going to steal a hydrogen from a different residue in the active site. That's going to act as a general acid to now give us the protonated Schiff base. And in the final step, water is going to come in, and it's going to hydrolyze the Schiff base, releasing dihydroxyacetone phosphate to then give us the regenerated enzyme. So that is the reaction in a nutshell. Okay. So the next reaction I want to go into is reaction number 6. So this is conversion of glyceraldehyde 3-phosphate to 1,3-bisphosphoglycerate. So I want to go over this reaction too, because you might have looked at this reaction and say, this reaction didn't really make sense to me. So I want to sort of step you through this reaction as well. So in this reaction, which is catalyzed by glyceraldehyde 3-phosphate dehydrogenase, we have, here's the active site, and we have NAD and a catalytic cysteine in the active site. Now when NAD is bound, it actually lowers the pKa of the cysteine to make it so that way it's now deprotonated. So it's in its thiolate form. So it's now more reactive. Okay. So what happens is we have glyceraldehyde 3-phosphate. It binds into the active site. And the thiolate, that's the cysteine, is going to act as a nucleophile. So it's going to attack the carbonyl carbon of glyceraldehyde 3-phosphate. These electrons are going to go into the oxygen. And now we form a tetrahedral intermediate. So in the next step, collapse of the tetrahedral intermediate is going to result in proton transfer of the hydrogen that's attached to this carbon to NAD. So this is where the oxidation reduction reaction actually occurs. So now we made NADH. We made this covalent enzyme substrate intermediate that's now been oxidized. And now the next step is to release that substrate to basically unlink it from the enzyme. So then in the next step, NADH is released. An inorganic phosphate comes in, and it's going to cleave the bond between the carbonyl carbon and then the sulfur on the cysteine. So the phosphate's going to do something called phosphorylysis. I think I'm spelling it right. There might be an extra Y in there. That means you actually cleave a bond by adding a phosphate. So the phosphate's going to act as a nucleophile. It's going to attack this carbonyl carbon. It's then going to break the bond between the carbon and cysteine to now make our product 1,3-bisphosphoglycerate and then regenerate the enzyme. Okay. So those are the two reactions that you guys need to know in glycolysis. which I feel like 2 is pretty decent because the other class they have to learn 4. So you can, I don't know if that makes you feel better or worse, that you're not learning as much as the other class, or that you have like, right, two less reactions to learn. Okay, so anyways, I just wanted to walk you through those reactions so that way you can kind of have a better understanding of why some of these intermediates are made in glycolysis. So, the pentose phosphate pathway, we're going to go over this pretty quick because there's not too much that I want you to know from it other than the important products of the pathway and one of the enzymes that gets regulated. So, the pentose phosphate pathway, also known as PPP, it's going to generate 2 important products. So it's going to generate NADPH, which is going to act as a reducing agent for fatty acid biosynthesis and cholesterol biosynthesis. So that's going to become much more important once you guys get into Biochem 2 and you begin talking about lipid and lipid metabolism. The other thing the pentose phosphate pathway produces is ribose 5-phosphate. Which is going to be used for nucleic acid biosynthesis. So NADP looks very similar to NAD+. So this is actually the structure of NAD+, except it actually has a phosphoryl group attached to the ribose ring. So this is actually NADP plus, which in order to make NADPH, it can react with 2 protons and 2 electrons to make NADPH plus H plus. So it's pretty similar in terms of the chemistry of NAD+, except it's going to be used for different things. So it being phosphorylated is going to give it a very, very different biological function. Okay, so the pentose phosphate pathway, we're going to go over it really, really briefly. I don't have my notes to this. Oh yes, I do have my notes, good. Not that I would have needed it, because there's so little I need you guys to know. I could have done it without my notes. Okay, so we start with glucose 6-phosphate. And this glucose 6-phosphate is actually really coming from glycolysis. So glucose becomes phosphorylated. So that's coming from ATP to make ADP in order to make glucose 6-phosphate. So what step of this is this in glycolysis? Yep, this is just step 1 in glycolysis, right? So it's just kind of just going through that same first reaction. So we have glucose 6-phosphate. And in the next reaction, an enzyme called glucose 6-phosphate dehydrogenase so it's a dehydrogenase, so you know that it's going to be involved in oxidation reduction. It's going to oxidize the alcohol into a C double bond O. So this is a redox reaction, oxidation reduction reaction. And NADP is going to act as an oxidizing agent to make NADPH. So then we form this intermediate that you don't need to know about called 6-phosphoglucanolactone. It then becomes hydrated to make 6-phosphogluconate. And then in the next step, that 6-phosphogluconate becomes oxidized. So this is going to result in another molecule of NADP being reduced to NADPH. There is then decarboxylation after that to make ribose 5-phosphate, followed by isomerization to make ribose 5-phosphate. So what you need to know about this, the pentose phosphate pathway, is it's going to make ribose 5-phosphate and NADPH. And then you just need to understand that this first step, that glucose 6-phosphate will become oxidized by glucose 6-phosphate dehydrogenase, and that NADP is going to be reduced to NADPH. That's all you need to know about this pathway. Well, it's more like that's all I want you guys to know about this pathway. So you can choose to know more if you'd like. Okay. So that finishes up glycolysis and the pentose phosphate pathway. Now I'm going to use the last 15 minutes to go over whatever I can of gluconeogenesis.